All right, welcome. Today, we are cracking open the roboticist's toolbox to get right to the heart of what makes any machine move. We're talking about motors. So, how do you actually bring a robot to life? It's a massive question, but honestly, it all boils down to one simple thing: movement. Whether it's a wheel spinning, an arm lifting, or a camera tilting, motion is everything. So, what's the secret to making it all happen? Well, the answer is the motor. And the best way to think about it is this: it's literally the muscle of the robot. It's the thing that takes electrical energy from a battery or a wall plug and turns it into real physical motion. But here's the thing: not all muscles are the same, right? A sprinter's legs are built differently than a powerlifter's arms. It is the exact same deal with robots. Some motors are built for speed, others for pinpoint precision, and some for just raw power. So let's open up the toolkit and see what we've got. Okay, first up, we have the absolute workhorse of the robotics world, the standard DC or direct current motor. This is really the most fundamental tool in our entire kit. So what's its job? Super simple. You just need something to spin. That's it. Think about the wheels on a small robot or a little cooling fan. Anytime you need continuous rotation without a ton of complications, the DC motor is your go-to. And don't let its simplicity fool you. The range on these things is pretty impressive. They can run on really low voltages, which makes them perfect for battery-powered projects, and they can get up to insane speeds like 20,000 RPM. But with that kind of speed, how on earth do you keep it under control? Well, the key is this really clever technique called pulse width modulation, or PWM for short. Instead of just being on or off, PWM acts like a super fast dimmer switch. You send these incredibly quick pulses of electricity to the motor. The width of those pulses, basically how long each one stays on, determines the motor's speed. Short, narrow pulses just give it a little nudge so it spins slowly. But as you widen those pulses, giving it more on time, the motor speeds right up. It's a brilliant way to get fine-tuned speed control out of a simple motor. So, the bottom line, for simple spinning tasks, the DC motor is a no-brainer. It's affordable, it's super easy to use, and controlling its speed and direction is a piece of cake. But, not everything is about just spinning around freely. What if you need more than that? What if you need to move to an exact position and stop on a dime? That's where our next tool comes in, the stepper motor. If you've ever watched a 3D printer work its magic, you've seen one of these in action. A stepper motor's whole job is all about precision. It's not about continuous spinning at all. It's about moving in these tiny, controlled, repeatable steps. A great analogy is the second hand of a clock. That perfect, accurate tick, tick, tick. That's exactly the kind of movement a stepper motor provides. A really common stepper motor moves in 1.8-degree increments. So if you do the math, that's exactly 200 distinct steps to make one full circle. Now, one of its superpowers is something called holding torque. This means that when it's not moving, it locks firmly in place. As long as it's got power, it is not budging. The main advantage here is that you get incredible precision without a lot of complexity. You can literally tell the motor, hey, take 83 steps, and you can trust that it did exactly that. This is what's known as open-loop control, and it works great for a lot of things. But that trust isn't foolproof. If you put too much strain on a stepper motor, it can actually lose steps, meaning it misses a command without you even knowing. They also use power just to hold their position, which makes them less efficient. And yeah, they can be a little noisy and whiny. So what happens when you absolutely cannot risk losing a step? What if you need to be 100% sure you're at the right angle? Well, that's when you reach for our next tool, the servo motor. A servo's job is simple. Go to a specific angle and stay there. Even if something tries to push it out of position, it'll fight back to hold its ground. Think of a robotic arm that needs to hold a specific pose, or the steering system on an RC car. You're not counting steps anymore. You're commanding a final destination. Now, what makes a servo so special is that it's basically a smart motor. It has its own little brain, its own control electronics built right in. So you get a complete package: a motor, a gearbox, a position sensor, and a controller. It always knows its own angle and is constantly correcting itself. This is what we call closed-loop control. It checks its own work. The benefits are pretty clear. You get a compact, all-in-one solution for incredibly precise control. You just tell it where to go, and its built-in brain does all the heavy lifting. Okay, and now for our final tool, What if what you really need is just raw power, top-end speed, and maximum efficiency above all else? Well, for the most demanding jobs, you need a powerhouse. And that is the brushless DC, or BLDC motor. This is the amazing technology that powers everything from high-performance drones to electric cars. The BLDC motor is all about performance, plain and simple. When you need the absolute best power-to-weight ratio, incredible speed, and efficiency that will last a long, long time, this is the motor for the job. I mean, these stats really speak for themselves. You're looking at up to 95% efficiency, and their lifespan is incredible because there are no physical brushes inside that can wear out. But all that amazing performance comes with a catch. It requires a complex external brain called an electronic speed controller, or ESC, just to make it run. So we've looked at the 4 main tools in our robotics kit, but how do you actually choose the right one, especially when you're trying to decide between the 2 precision motors, the stepper and the servo? This is a classic robotics dilemma, so let's put them head to head. A stepper motor is open loop. It just assumes it's in the right position by counting steps. A servo motor, on the other hand, is closed loop. It has that internal sensor, so it knows its actual position. Another huge difference is that a stepper can rotate continuously, 360 degrees, all day long. A standard servo, though, is usually limited to a 180-degree range.
Okay, let's put it all together in a final showdown. Think of this as your cheat sheet. For simple spinning, a DC motor is your best bet, period. For precise, repeatable steps and great holding power, you're going to want a stepper. If you need to hold a specific angle and fight to stay there, a servo's the way to go. And for maximum power, speed, and efficiency, well, the BLDC motor is the undisputed champion. So, we've explored the fundamental muscles of today's robotics. But as robots evolve, as they get softer, smarter, and maybe even a little more like us, what new kinds of motors and actuators will they need to power the next generation of movement? That is something to think about. Thanks for joining me for this one.